Welcome back. In this lesson, I want to talk about optimal inventory management. But what is inventory optimization? What are the questions we should be asking? And how do we know that we are managing the inventory in an optimal manner? So the first question obviously we need to ask is how much to order, right? And the second one is when do you want to order? When should you order in order to ensure that the inventory is at an optimal level? And the third is how do you go about controlling your inventory system in order to ensure that you are at an optimum level? Now, these three things are at a tactical level. Once you figure these things out, an optimal set of inventory management will emerge out of it, right? So, and how do we measure the inventory performance is optimal? And so these are the two things we would look at: service level and inventory investment. So these two are contradictory requirements. Okay, if you want to keep a lot of inventory, you can provide a good service level, maybe 100%, but then at the cost of inventory investment. On the other hand, right, so if you want to minimize the inventory investment, then your service levels would suffer. So you need to balance these two, and you need to operate at an optimal point while you're balancing these two based on your requirements. And when you do that, you would maximize the return on the invested capital. So our goal is to improve the service level, reduce the inventory investment. And you can't do this with zero inventory and 100% service level. You can't achieve that. There is a threshold beyond which you can't go further. And we want to determine that threshold. I will talk about that, right? But the point is really maximize the service level and minimize the inventory investment till the point of optimization, right? In order to increase your return on the invested capital. That's the crux of the whole subject of inventory optimization. So let's begin with the question of how much to order. This how much to order question drives two things. Number one, obviously the quantity that you order, which is the very question. But that also means that, if you change the quantity, the order frequency changes, right? So for a quantity of 50, for example, there are 6 times in this picture you see we are ordering, as opposed to if it is 100, you will only order 3 times. You can see the curve, the sawtooth curve going up and down, etc. When it comes up actually in a straight line, when it comes up, what it means is that you have received the replenishment of the stock, and then you're gradually going down because daily demand is eating away the stock, and again you come back, right? So the order frequency and quantity, these two things determine different kinds of costs based on which it has been proposed that we should optimize the order quantity based on these two competing cost elements. And that's where this economic order quantity comes. Now, the focus of my lesson today is not about the economic order quantity because this is an old concept. It works, but it has a lot of problems. I will just introduce this to you now, and then we will move on further on this particular question of how much to order. Now, economic order quantity basically deals with the total cost with respect to the order quantity, and so the ordering costs actually come down as you increase the order quantity. If you, for example, reduce the order quantity, the frequency of ordering increases, and therefore the ordering costs go very high, towards the left side of the curve, as opposed to high quantities where there is less ordering cost because you have too few orders. Very simple. On the other hand, you also have a holding cost, right? The more you have the inventory, the higher the holding cost, or rather, if the higher the order quantity, the higher the holding cost, and the relationship is proportional. I don't want to go into the mathematics of it. We will touch mathematics subsequently, right, and in more advanced concepts, because I will just mention the formula, how to calculate, rather than trying to derive it. But yes, we will deal with a lot of mathematics in this particular lesson. So the total cost then is a sum of these two lines, the green line and the red line. If you sum them up point by point, right, this is what you get. That's the total cost. And what you really need to do is to find out the minimum. And that minimum is actually done through a mathematical method where you do a partial differentiation and then find out the minimum. Don't worry about all that stuff. We know what the formula for EOQ is. That's how they find the minimum. And the order quantity corresponding to that minimum cost line on that blue curve, on the total cost curve, is the economic order quantity, EOQ. And that is given by this particular formula, EOQ equal to square root of 2SD over H. And what is S? S is the ordering cost per order, right? For example, if you order 10 times in a year or 12 times in a year, your order cost is the ordering cost times 12. If you order it only 6 times, it's less, etc. So the ordering cost per order is S. D is the annual demand, the total demand during 1 year. And H is the holding cost per unit. Now, it is not the multiplication of the unit price times the total quantity that you order, but we consider the opportunity costs, and that's why I want to talk about the bit of a detail on these types of costs. So ordering costs generally are determined by the order frequency, and they include things like purchase ordering, admin costs, shipping and transportation costs, right? And the thing is that if you group the SKUs, you can reduce the shipping and transportation costs, receiving costs, accounts payable admin costs. So the PO admin and accounts payable admin can be actually reduced or even eliminated, almost negligible, when you put in automated systems. So these are the typical ordering costs. As for holding costs, which are determined by the order quantity rather than the order frequency, we have opportunity cost. So opportunity cost is like, for example, if a part costs £10 and you ordered 100 of them, so that's £1,000. So £1,000 of worth of inventory you're keeping, which means that you would have invested that elsewhere if you had not kept it, and therefore you multiply it with the interest rate, say 10%, and the 10% of the 1,000 would be 100, and that is your opportunity cost. Okay, so and then you can also add to that the storage cost and obsolescence cost, and sometimes the price of the items actually decreases based on the discounts if you order in more quantity and higher quantity, and therefore you need to potentially include that as well, but we have not included that in the formula we just discussed earlier. But these are the types of holding costs. Okay, essentially the EOQ talks about balancing the ordering costs versus the holding costs and finding that sweet spot in between to ensure that we have the right quantity with a minimum cost. Now there are some issues with the EOQ. Okay, these are the key issues. There are several, but I will emphasize on 3 things. Key issues with EOQ. Number 1, EOQ does not take production capacity or supply capacity into consideration. Okay, what does it mean? It means that if you say, if we come up with an EOQ of 10,000, so it is taken for granted that, okay, if we order 10,000, the supplier is able to provide the 10 or supply the 10,000 or produce the 10,000. That's the point. And secondly, the demand is constant. We talked about annual demand, D being the annual demand in this case. So demand is constant, it can't vary with time, and is deterministic, not statistically varying or stochastic. So this model doesn't really account for the day-to-day statistical variation of the demand or week-to-week variation of demand, etc. So it assumes pretty much it is constant, and secondly, it is deterministic, that it can be determined. Thirdly, which is linked to the first question, when to order question is not addressed by EOQ. And why is this important? Because, if we say, for example, okay, the EOQ is 10,000 and the supplier may be able to supply, but not in the given time. Here actually EOQ doesn't even assume any amount of replenishment time as such. Actually, according to EOQ, the underlying assumption of the EOQ is that the shipments are received instantaneously when they are ordered. In other words, the sawtooth curve keeps on going. The moment you order, you get it next second or even in the microsecond, right? And then that's it. So EOQ doesn't care whether the supplier can produce or ship that many quantity. It doesn't account into consideration the replenishment time or the production time that is involved. And so what are you going to do with the EOQ then? So there's a major problem with the EOQ. So that brings us to the second point, when to order. So this when to order point is not at all addressed by the EOQ, if you remember our discussion in the previous slide. So let's talk about when to order. So let me show you this graph here. The blue line there, the sawtooth curve, represents on-hand inventory, and that's the one that we saw in the previous chart, where we saw two different sawtooth curves, one with a higher frequency, lesser order quantity, and the other with a higher order quantity and a lesser frequency. Right now, there is another line there you can see in gray called in position, which is inventory position. Now we define a new term called inventory position, which is basically a sum of on-hand inventory, that is the real physical inventory count that is present in your warehouse or in the place where you store the goods, plus the amount on order. The amount on order means the number of orders that you have already placed but you haven't yet received. Okay, and then you subtract from it the number of orders you have received from the customer but you haven't been able to serve yet. So if you do this math, what you get is an inventory position. Here in this particular chart, you have the back orders equal to 0, and therefore your inventory position is pretty much on hand plus on order. What happens to that gray line is that it shoots up in the middle somewhere while the on hand is still going down. What does it mean? It means that an order has been placed there, and then it goes up and keeps coming down and then joins back at the point when the blue line comes back. So the time difference between the gray line going up and the blue line going up is the replenishment time. But we will talk about all of those one by one. So this is the inventory position. Now, using this inventory position, we can determine the question about when to order. We need to introduce a few more terms here. Okay, the first one is reorder point. Reorder point. So what is the reorder point? So what we do here is we take the minimum of the inventory position. The inventory position is going up and down, right? Take the minimum of the inventory position and the zero position. That distance is the reorder point. What does it tell us? When the inventory position is equal to the reorder point, we place an order, and that's why the inventory position immediately shoots up. The on-hand inventory doesn't shoot up immediately. It shoots up a bit later after the replenishment time. And that brings us to the definition of replenishment time. So that's the replenishment time there in between, RT equal to 10 here in this case, right? So it is the distance on the horizontal axis between the point when the inventory position goes up and after a few days here, the on-hand position goes up, which means that an order has been placed, and after 10 days an order has been received, and therefore the on-hand inventory goes up. Remember, in EOQ, replenishment time equal to 0. Okay, so this is why EOQ doesn't work, except for maybe simple trivial problems. Really, you need to consider this question of when to order, and the when to order question depends on your replenishment time, and ROP is pretty much the when to order point, right? Because when the inventory position is at the ROP, when it tries to fall below the ROP, or is it at the ROP, you place an order. That's the when to order question. Let's bring in another term called replenishment time demand. What is that? Now, we've already seen ROP and RT, replenishment time. As you can see here on the chart, I've grayed them out, but you can still see them. Now, consider the minimum level of inventory position. I've drawn that minimum line, okay? And now consider the minimum position of the on-hand inventory. So we have two minimums, the minimum of inventory position and the minimum of on-hand, right? Inventory on-hand. So the difference between these, or rather the gap in between these, is the replenishment time demand. What does this really mean? It means that during the replenishment time, remember, and look at the chart there, during the replenishment time, the blue curve continues to fall, right? It keeps going down. And therefore, it goes down by an amount, by a certain amount, which is equal to RTD, which is 50 here. In other words, a 50 unit demand has risen during the period of the replenishment time. So replenishment time demand is essentially how much demand has occurred while the order was still open, right? We placed an order for replenishment, but it is still open until the point it is, until the point it is shipped, right? Or it is received. So during that time, how much demand has occurred, and that's the RTD. So in EOQ, again, in economic order quantity, replenishment time demand equal to 0. Why? Because the replenishment time equal to 0. Another term, these are all linked up, okay? They are all linked up through math, and I will show you the math as well a bit later, right? Another term now we will introduce is the safety stock. Safety stock. The safety stock is the distance between the minimum of on-hand inventory, okay, I have marked it there, minimum of on-hand inventory, and the 0 line. So you can see the safety stock equal to 2. That arrow there going up from the red line to the other line is the safety stock. Oh, by the way, this red line is not the 0 line, but the line behind it, because back orders can be negative, and therefore you will see sometimes it going down. In this case, back orders are 0. So what is safety stock then? So safety stock is essentially, you can see there, ROP minus RTD is the safety stock. We already have that ROP marked on that chart there, and the RTD. You can see geographically, geometrically, safety stock equal to reorder point, which is ROP, reorder point, minus replenishment time demand. Okay, and what is replenishment time demand? Replenishment time demand equal to the mean, the average demand per day, and the number of replenishment days. If you just multiply them, you will get replenishment time demand. All right, now you might have noticed that this is pretty much uniformly going up and down. There is not much of a variation. There's not much of variation in the demand, and there's no variation in the replenishment time. But really, in the real scenario, you will have demand variation and you will have variation in the replenishment time as well. And so if I introduce variability and simulate this once again, I get a chart something like this, where you can see the bottom level of the blue curve in the first cycle is a bit higher than the bottom level of the blue curve on the second cycle. And so this replenishment time demand RTD has a different value on different cycles, and the replenishment time itself, RT itself, has different values at different cycles, which means it is a statistical variable, and the sawtooth is not exactly uniform and plain. It goes up and down a little bit based on your demand variation and based on the variability in the replenishment time. The demand variability is coming from your customers, and the replenishment time variability is coming from your suppliers. All right, so let's move forward. Now, let us analyze a bit what happens to this sort of a chart going up and down, this inventory sawtooth, when the reorder point is greater than the replenishment time demand. Let us go back quickly. You will notice that in this safety stock calculation, right, the replenishment time demand RTD is lesser than the ROP. ROP is 70, RTD is 50, and that's why you have a safety stock positive, which is equal to 20. What happens when ROP is lesser than the replenishment time demand? You see here is RTD is 50, but ROP is only 40, and so you have a sort of a negative safety stock, so to say. And what does it mean? It means that you'll consistently show back orders every cycle, assuming if this is a uniformly going up and down sort of a situation, right? So with not much of a variation in demand and replenishment time, then you will consistently, in every cycle, in every up and down that you see there, in every cycle, you will see back orders like you see here, right? So that's what will happen when reorder point is less than the replenishment time demand. What happens when the reorder quantity, oh, by the way, reorder quantity is the amount by which the blue line goes up in every cycle. The vertical distance between the bottom point and the top point of the blue curve is the reorder quantity, because that's the amount of order that is placed, and so when you get replenished, the stock level goes up by that amount. Now, when this reorder quantity is less than the replenishment time demand, ROQ is less than RTD, you will see something a bit stranger. What you see here is that, okay, so let me first show you something. So we've got this minimum level of inventory position, that's the ROP, and from there we draw the line and we get an ROP, reorder point of 70. But the the replenishment time demand RTD of 50, and then finally ROQ reorder quantity of 40. What's happening here is that and of course this RT equal to 10 is the distance. Now what happens in this situation is the order placed in the previous cycle gets replenished in the next cycle. That's what happens. When you try to reduce your reorder quantity too much, then you will move behind into one cycle, or you place an order in this cycle, then the replenishment for this cycle must come from an order placed in the previous cycle, and then the order placed in this cycle will be replenished in the next cycle. This becomes a bit trickier, and in fact, if you try to reduce ROQ too much, it might jump into 2 cycles or 3 cycles. In other words, when you place an order now in this cycle, you will get the order replenished after 2 cycles or after 3 cycles. This system also can be implemented, but you need to be able to predict with more high level of accuracy whether it works. And also, there is a bit of an initial stabilization that is required. Remember, your first replenishment is coming from your previous order in the previous cycle. So obviously you have to start from somewhere, and when you start from somewhere, there are no orders placed, and therefore what happens is initially you will see some back orders, but later on, as you keep on placing orders, your situation will improve, and then you will stabilize into a scenario that is shown in here. Essentially, when ROQ is less than RTD, what happens is that the order placed in this cycle will be replenished in the next cycle, and the replenishment of this cycle comes from an order placed in the previous cycle. And it could be a cycle before that as well, depending on how low is your ROQ. And therefore, again, we will try to avoid such a system to design, but doesn't mean it can't be done. It can be done, provided you have an ability to crack the math. What I have here is a simulation that I have written in our programming language, and that's the result. I can churn the numbers quickly and show you what happens when you change all these numbers. But if you want to apply to your inventory situation, it can be really difficult unless you have good tools with you. And so the recommendation is to ensure that ROQ stays above RTD, so that when you place a replenishment order, that you get it. What happens is, when the ROQ is less than the RTD, it will not replenish sufficiently. Therefore, you need to place another order, and then that will come through only in the next cycle, etc. That's what happens in this scenario. Okay. Right, so let's come to the last question of how to control. We talked about how much to order. We looked at EOQ, economic order quantity, and we looked at when to order, and we introduced a term known as ROP, reorder point. So that's the point at which we reorder. So that addresses that question. And now we come to how to control. How do we control the whole system? The way to control is simply using the inventory position. We defined the inventory position already in one of the previous slides. Inventory position equal to on-hand inventory plus on-order inventory. Inventory on order, you place it in order, and that's the quantity, minus back orders. Back orders are those orders which have come through, but you haven't been able to serve them yet. As in, the order is still open, the fulfillment has not yet been done. So if you keep on tracking your inventory position, this is a continual tracking position. Okay, so you keep on tracking this on an ongoing basis, which means that your IT systems should be able to track every outgoing and an incoming part and demand item, etc., so that you have a complete track of everything. The point is not just having a track of everything. You see, there are a lot of inventory software which basically track everything. And not only track, but also some of the software, they also calculate the reorder point and reorder quantity, but their methods are very, very crude, and they may not be the best things that are available here. So let's talk about this one. So how do you control? So what we do is we keep on a continual basis monitoring the inventory position, right, item by item. Okay, ensure that the inventory position will never fall below ROP plus 1. In other words, the moment it reaches ROP plus 1, you place an order. So at ROP, essentially, plus 1 is just the safety there. But you can say at ROP, you place an order, right? And then because you place an order for an amount of ROQ, that's the reorder quantity, the inventory position will never exceed ROP plus ROQ. Okay, that's about it. And so that's how you control the inventory position. So essentially, the model that we have been looking at, right, using the reorder quantity and the reorder point, is a better model. And the problem we try to address using this is, what is the optimal ROQ ROP combination? So ROP is essentially the distance between the zero line and the minimum level of inventory position, and ROQ is the reorder quantity. You can see that as the distance between minimum and the maximum of the on-hand position, right? So what are these two values? What is the optimum configuration of these two values? By the way, this model is also known as a QR model, where Q represents ROQ and small r represents the reorder point, ROP. Okay, now this model essentially has resolved the issues that were raised in the EOQ discussion. We said EOQ does not take production capacity or supply capacity into consideration, but now by introducing the replenishment time, we can absorb this. If they can't produce instantaneously, they can produce in a day, if not in a day, in 10 days, right? So put in the replenishment time for the quantity you want to order. Number 2, demand is constant and can't vary with time and deterministic and not stochastic, etc. Now that is sorted. You have seen that we can actually allow demand variation, variability, and replenishment time variability. I also have shown you a chart where the things vary, have a variability, and therefore you can see the differences of replenishment time and differences of the RTD, or the replenishment time demand. And thirdly, when to order question was not considered. We have the answer, and the answer is ROP, reorder point. That's the answer for the when to order question. Now that we have addressed all these three things, we come back to, so how do we know that we have the right optimally managed inventory? So to address this question, let me introduce to you the concept of efficiency frontier. Inventory efficiency frontier. It is basically a curve that is plotted against the fill rate on the horizontal axis and the total inventory investment on the vertical axis. Fill rate is essentially what is the percentage level of your ability to fulfill the orders of the customers, right? So in other words, talking in terms of inventory, when an order arrives, have you got the stock to fulfill the order? If you haven't got if you haven't got 5 times in 100 occasions, then your fill rate is 95%. Okay, and the total inventory investment is obviously the total inventory investment of all the items that you have stored. And we can analyze an organization or a facility or anything and come up with the total efficiency frontier chart, something like this. And what does this represent? It represents the best possible scenario positions of inventory investment and the fill rate, beyond which you cannot get to. So let me illustrate this. Suppose, say, this is your current position. In other words, you're roughly having a fill rate of 60%, but quite a high level of inventory investment. What you would want to achieve is, say, while maintaining the same fill rate, you could potentially cut down your total inventory investment by a large amount. Or while keeping the same level of investment, you can drastically improve your fill rate to the point of B. Or you can take a trade-off in between and then still get a decent level of fill rate and then also substantially reduce inventory levels. What this curve, the blue curve also means is that you cannot go past that blue curve. So that point is not possible. Okay. So in other words, that blue line is essentially the boundary line beyond which you cannot go, and you can decide the point of operation where you can operate. And your current position may be totally off the curve. It may be outside. Most likely it will be outside the curve. You want to get onto the curve, and you want to make a policy decision as to how much fill rate do you want to do, and then how much inventory investment do you want to carry. Because obviously, as you approach, when you say, if I want to get 100%, yeah, it is possible. No, it is not possible, because the inventory investment will go really, really very high, mathematically speaking, to infinity. Okay. And why is that? Because you may get a sudden huge amount of demand in the next day, and because of the variation, and then let's say the whole of a 2 years demand comes now, and for the next 5 years there is no demand. Let's say what happens? That's the extreme case of high level variability, in which case you won't be able to get the 100% fill rate, right? So that's the point. So as you approach 100%, your level of inventory investment goes really high. So how do you ensure that you fulfill the customer SLAs 100%? You can do that by agreeing, again, having a policy of what do you call the lead time policy. The lead time can be fixed. It's not the replenishment time, but the lead time with the customer. You can decide 1 or 2 days or whatever, and give a buffer so that you can handle you can handle it with a 97 or 98% and have a practically low levels of inventory. The point is really you need to decide a point on this particular curve. You want to move to the curve, and you want to decide a point on this curve. And one of the things that you can think of in deciding the point on the curve is the impact on the ROIC. Sometimes if you give less fill rate, then you might impact the customers. And can you do that? How are your competitors doing? And it might affect the revenue, etc. So taking all these into consideration, and we cannot easily establish a mathematical relationship unless we know a lot of things in a given organization, but it might be possible, and it differs from company to company. Therefore, the key thing is really, how does it impact on the ROIC? That's the key consideration that you need to keep in mind in order to get to the policy point of where do I want to operate at a fill, as far as fill rate is concerned. So coming back to the efficiency frontier. Now, let's say this particular point on this particular point, right? Each point on this corresponds to a way of, a decision. Each point on this is essentially a combination of ROQ and ROP, etc. And that has a certain behavior. And you can see there the fill rate in this particular behavior, it has a bit of a negativity, therefore it is about 99% or whatever. And then you also have an average level of investment. And so using this fill rate and average level of investment for a given combination of ROQ and ROP, you can plot that efficiency frontier. Okay. Another thing about the efficiency frontier is the impact of ROQ on the efficiency frontier. When you change the reorder quantity or the quantity of order, right, what happens? So the reorder quantity can impact it like this. For example, if you were to plot the efficiency frontier only for one item, let's say, you have to actually do it for the whole of the company. That means all the items and the parts. But let's say if we do for a single one, or you can replace the ROQ with the order frequency. That's one and the same. So what is the impact of reorder quantity or the order frequency on the efficiency frontier? As you increase the ROQ, the efficiency frontier raises up. In other words, the requirement for inventory investment goes up. Okay, it's vice versa for the order frequency. And how does ROP impact the efficiency frontier? So ROP is essentially, once you decide the level of ROQ, the level of ROQ will decide which line is it. And once you decide which line is it, where are you on the line is determined by the ROP. Lower the ROP, you'll be towards the left side, which means lesser fill rate. And higher the ROP, you'll be towards a higher fill rate. Okay. And remember, ROP determines the safety stock as well. And therefore, higher the safety stock, higher the fill rate, lower the safety stock, lower the fill rate. Now, the question is, how do we generate this efficiency frontier? How do we generate the efficiency frontier? We need to consider these variables, okay? We need to understand what variables are there and how do we play with them, how do we run the math. First of all, you have external factors of demand and replenishment time. Demand is determined by the customers, replenishment time by the suppliers, and the values of demand and the variability of demand, the value of replenishment time and the variability. All these are the variables that we need to take into account in order to construct that the inventory efficiency frontier. Plus we need policy variables. Policy is something in our hand. We can decide. We can't play with the demand and the replenishment time. To some extent we can control, but policy variables are very much in our control. We can decide, and that is reorder quantity, what is the ROQ, and what is the reorder point, ROP. And using these two, of course, you can also calculate the safety stock, which is it's one of the, once you determine the ROP, it doesn't matter what your safety stock is, it is a consequence. Okay, you can play the other way around as well. You can decide the safety stock and then calculate the reorder point. It's one and the same. So those are the policy variables. Now and the results will be, then you can calculate using all these 4 known values. You can calculate the calculated values, which are fill rate and inventory investment. So the fill rate and inventory investment for various combinations of all these values, well, demand and replenishment time, we take it as it is, item by item, and then based on a range of values of a reorder quantity, a range of values of reorder point, we can figure out what is the fill rate and inventory investment, and then determine what is the best possible result we can get, and that is the efficiency frontier. Okay, that's how we do the efficiency frontier. We want to increase the fill rate, we want to reduce the inventory investment. So let's take an example here. I'll take an example and show you how I have generated an inventory efficiency frontier. Now let's take demand and replenishment time. So this is the demand distribution with a mean of 5 units of demand, with a CV, which is a coefficient of variance of 0.2. Well, there are different ways in which you can measure the variability in terms of standard deviation, and variance, which is standard deviation square, or CV, which is standard deviation over mean. CV equal to 0.2 here. Now what I'm going to do is I'm going to use later on a gamma distribution. I don't want to confuse you, but if you use a normal distribution, sometimes you might get a negative values, and there is no negative demand, no negative replenishment time, and no negative quantities in the inventory. Therefore you need something which positively closes on from 0 onwards to the positive rather than negative to positive. Okay, and that's why the normal distribution may not work, especially for lower values. So although this CV equal to standard deviation over mean, I'm not going to use a normal distribution. I will use something known as a gamma distribution, but that is beside the point. So these two are the distributions, and the average demand, DD, is the daily demand, and average replenishment time. When I multiply, I get an average replenishment time demand, RTD, remember, and I simulate a bunch of values of demand and a bunch of values of replenishment time and multiply them, and I get a bunch of RTD values, and I plot them like this, and that's the distribution of RTD itself. In other words, the replenishment time demand itself keeps on varying from cycle to cycle, as we have observed in one of the other earlier slides. Now, how do we calculate the fill rate from here? So using this, we need to calculate the fill rate. Here we have the distribution of RTD, replenishment time demand. And let's say this is the average RTD, average replenishment time demand. And of course, the yellow curve is the probability distribution of the replenishment time demand. Let's say our inventory position is at the value of ROP, right? So these are the back orders, and this is the fill rate. But remember, the inventory position varies from ROP plus 1 to ROP plus ROQ. Therefore, you can actually vary this ROP point all over the place and take an average of that value. So essentially, you could use this approach. Now this red area corresponds to ROP. If you increase the ROP slightly more, your red area comes down, etc. So what we really need to do then is to change that value from a bottom to the top, as in, of course, this is the safety stock. So this is the fill rate formula. So what you do is you calculate the cumulative probability from ROP plus 1 to ROP plus ROQ and sum it up and then divide it by the ROQ, and that gives you the fill rate. So what we're doing is we are using the principle of inventory position, which varies from ROP plus 1 to ROP plus ROQ, and that is the reason why we have the formula in this manner. Now we also have calculations for the inventory on hand. Inventory on hand equal to half of ROQ plus ROP minus RTD. This is when ROP is greater than RTD. If ROP is less than RTD, okay, we use this alternative formula because we do not count the back orders in the part as a part of the average on hand inventory. Okay, and that's why the formula changes. This has been derived by mathematics, but don't worry how we got this, but it's accurate. Right, so let's say there is an organization which has a bunch of SKUs. In this example, let's say 12 items, and they have different unit costs, and we have analyzed and obtained the mean and the variance of demand and the mean and the variance of replenishment time. So mu dd is the average demand and CV is the coefficient of variance. So coefficient of variance of demand and coefficient of variance of replenishment time. And what is the coefficient of variance? It is the ratio of standard deviation to the mean or to the average. So we get this data from their order data and the supplier data, right? And we analyze and fill this table. We also obtain as is ROQ and as is ROP. With this data in hand, we can use the formulas that I have mentioned earlier to calculate as is fill rate and as is inventory cost, which in this case turns out to be 80% of fill rate and 107,000 pounds. Now, is this acceptable? No, 80% may not be sufficient, so we may have to increase it, or we do not know if this inventory cost is good enough, whether it needs to be reduced. Let's look at the options. So first of all, we can't any longer go with the as is ROQ and as is ROP. So we need to find new values for them for this table. So we need to find ToBe ROQ and ToBe ROP, and then find the new fill rate and a new investment cost. So let's begin by analyzing for the ROQ, the ToBe ROQ. Okay. So what I do is I calculate the economic order quantity using this formula, and I use S equal to 100 pounds, and demand is obviously 252 days. That's the number of days in the year. So the annual demand is the daily demand times 252. So I calculate that, and H is the holding cost, which is 10% of the unit cost, which is the same as the opportunity cost. And so I put those values in that formula. I get an EOQ value for each item. Can I take EOQ value and proceed? Perhaps not. The reason being, remember I told you earlier that if your ROQ is less than RTD, then the order that you placed in this cycle will not arrive in the same cycle. It'll arrive in the next cycle, and that will pose a problem in managing the inventory position, in managing the system, and you need a bit more accurate analytics to handle that situation. It is possible, actually, it is definitely possible to handle that. But what happens is that you need to place a series of initial orders so that they will serve the demand that will arise in the subsequent cycles. Okay, and so at any given time, an order placed in a previous cycle, previous first or the second cycle, will actually get replenished in the current cycle. Okay, that's how it will work if the order quantity is less than RTD. We'll try to avoid that situation in this exercise, and so what I do is I take the maximum of EOQ and RTD, and what I'm trying to do is if EOQ is greater than RTD, I'll keep the value, or else I'll take RTD, which is the same as saying take the maximum of EOQ and RTD, right? So I have the EOQ values. So we have the ROQ values. So as I've been saying earlier, we need new set of ROQ values and we need a new set of ROP values to be able to calculate the overall fill rate and overall investment cost numbers. So at the moment I have only a new set of ROQ. I don't have a new set of ROP. So how do I decide that? So instead of deciding the new set of ROP, what I'll do is I'll take a range of values of ROP across the board and solve the problem and get a series of values of fill rates for various fill rates for different ROPs, and I get a curve like this, which is an efficiency frontier. So this blue curve here is the efficiency frontier, which is plotted for the ToBe ROQ values that we have in the last column, max of EOQ and RTD. Okay, those values of ROQ, the reorder quantities, from that column we have taken the new values and we've plotted this blue curve. Now each point on the blue curve corresponds to a certain values of ROP for all the items. So we kept on changing those values over a range of values of ROP and we got a curve. Right, so this is the combined efficiency frontier. When I say combined, it is combined for all the 12 parts. This we got in literally under a minute for 12 parts. Actually, I ran 100 parts and I get it not under a minute. I mean, this is literally in say, a few seconds. In under a minute, I can get it for a list of 100 parts, which means 1,000 parts I can run in 10 minutes. On the R calculation using R, basically, using the same formula that I have described earlier. Right, so we have this blue curve, which is the efficiency frontier. But what is this red and green curve? I've also created additional efficiency frontiers for 2 times the ROQ scenario and half the ROQ scenario as well, just to see how does it look like, so that in case if we choose to change the ROQ values, we know where we will fall and what are the ranges of this in case we choose to do so, right? And that red dot is the as-is position of fill rate of 80% and investment cost of 107K. Now 80% is obviously not adequate and therefore we need to improve. So looking at the curve, looking at the blue curve, we could potentially move towards the right, and if we go to 100%, if we go towards 100K line, say, we can reach almost roughly around 94% on the blue curve. That is not sufficient. Maybe I think we should try 98%, and what I do is I'll set 98% in my calculation and figure out what is the corresponding values of ROP for all these items if I were to have a fill rate of 98%, and this is what I get. So for a given fill rate of 98%, I calculate ToBe ROP values for all the items, and of course the safety stocks also for all the items. How do I get the safety stocks? By subtracting replenishment time demand from each of the ROP values, I get the safety stock using the formula which we discussed earlier. And then of course you can calculate the total inventory cost as well as usual, and that will give you a certain figure. Now there is a problem with item 6. It shows a negative safety stock, and that may be because of 98% in that particular one. is actually showing a negative safety stock. So let me correct that. If I were to add 158 and 52, I will get 210. So I correct that value 210, make the safety stock as 0 and recalibrate the whole thing, and I get a new set of values. There's a slight change in values, which is pretty much almost a couple of £100 of difference, slight difference. And so the total cost is around 127k now, and 98% of fill rate. And so on the combined efficiency frontier, then I have moved from a 80% to 98% position. And have I saved any inventory cost? No, in this case I have not saved. I've actually gone up slightly by 20k. But the point really is it is optimizing the inventory. That doesn't mean necessarily cut down the inventory. If you may be losing a lot of customers, in this case you might gain a lot of revenue or keep the revenue and don't lose the contracts because your fill rate has improved, and you can play with the SLAs slightly and make it 100% by giving a bit of a lead time for the customers, right? But 98% is a lot better than 80%. Operating at 80% will be very bad. And therefore, obviously, with this new improved scenario, you could improve your revenue situation, and therefore the additional profits can help you fund this additional investment cost, and that will have a better return on the invested capital. So you need to really work out the numbers and see whether that makes sense or not. But the point here is in this example, we have a lot of improvement in fill rate, but slight increase in the investment cost. Just imagine if I were to cut down the ROQ by half, then I come to the green curve, and so if that green dot there, if I come down on it onto the green curve, then I can actually get a 98% for a much lesser, for about 100k, you can say roughly. So slightly reducing the inventory cost by 7k, but at a higher ToBe ROQ. Now notice in the last in the calculation we did for the ToBe ROQ, we did not allow the ROQ to fall below the RTD. But if we try to increase the ROQ or cut down the ROQ by half, then it will fall below the RTD, which means that the replenishments will arrive in the next cycle or the cycle after. And that's fine, but that can be managed carefully. That has to be managed carefully. So the point that I'm trying to illustrate here in this lesson as we end this is that we need to have something like this, a efficiency frontier, which will help us to decide on which point are we going to operate, and then work out the numbers and decide what is the ToBe ROQ and what is the ToBe ROP, and implement that policy for every single SKU. And we might say, okay, do we need to follow ABC analysis? Maybe we have to. But the point is, with the computational capability that is available, you can literally crunch these numbers and calculate a policy for every single SKU, unless they are literally if they are in hundreds of thousands, and if we are not able to run the numbers quickly, then that's a different case. We could just maybe bunch them up together and then do by classification. But otherwise, in this case, as I said, I ran 12 items in literally 7 or 8 seconds, and with under a minute I can run 100 items. 1,000 items would be, I would imagine, about 10 minutes or so. So 10,000 items I can do in 1.5 hours. Or you can say 100 minutes. No, 10 minutes. Yeah, 100 minutes, which is like 1 hour 40 minutes. Not bad. 10,000 parts, 10,000 SKUs can be run under 2 hours. And if I run overnight, then let's say 4 times of that, which is like 40,000. 40 to 50,000 SKUs we can run overnight on my Mac with a simple R-based code, which pretty much runs the formulas that I have shown earlier. And I'm using, of course, the distribution is the discrete gamma distribution that I use. But yes, that's the approach. The key is to figure out the ROQ values and ROP values for us to ensure that we are in an ideal position, or we are in a better position on the efficiency frontier. I will talk to you again in the next lesson.